right, so we're talking about the solvation of polar solutes in polar solvents. What I have here is a solute, table sugar. You know that table sugar can be dissolved in water. And it's going to be dissolved in a different fashion than the ionic solute we talked about earlier. Okay, it's still going to be dissolved, but it's a different process. And you also know, I think, that table sugar forms crystals. Okay, so we said that with the ionic compound, when we're drawing the structure of that, and we showed how it gets dissolved, we said that at each corner, water molecules can pull them apart through that process of solvation. So here we're going to look at how the process of solvation works when we have a structure like this. Okay? So at each one of these OH groups, that's very similar to the structure of water itself. Remember that water is a bent molecule, and we have hydrogens that are covalently bonded to oxygens. And then when we were doing three-dimensional structures to figure out polarity, we also figured out that there were these lone pairs of electrons sitting out here as well. Okay? Well, each one of these OH groups are very similar. Now, we're going to attach the OH group to any kind of carbon chain, and the symbol we're going to use for any carbon chain is R. R is a symbol that means any carbon chain. So, for R to be attached to an oxygen and attached to a hydrogen, the structure is very, very similar. Okay? So any one of these OH groups on here, that's just like this. Pretty much yes, like I took an H off of a water and stuck it on a carbon chain. I mean, that's kind of what's going on. Okay? Since water we talked about in the last unit, and it's some in this unit as well, water is really strongly attracted to itself because of this hydrogen bonding capable situation, this structure where oxygen and hydrogen are attached to each other, and there's a really strong polar thing going on there where most of the electrons stay around the oxygen. It creates a partially positive and partially negative end of the water. We talked about that. So that water is partially positive where the hydrogen is located, and partially negative where the lone pairs on the oxygen are located. So those positive ends here are attracted to other waters. Well, it's also going to be attracted to this group. So if I have this structure where R, any carbon chain, is attached to an oxygen, which is attached then to this hydrogen, I've got these lone pairs of electrons here. Then it's possible for this hydrogen then to have hydrogen bonding to another oxygen where there are lone pairs.
Yeah.
And so what we have here is hydrogen bonding going on. And there's hydrogen bonding going on down here as well. But these lone pairs then are attracted to the hydrogens on water molecules. So everywhere there's one of these OH groups on a carbon chain, there are 3 places for water to hydrogen bond, a very strong attraction. Okay? All right, let's compare this then to the structure we actually have in our drawing. Let's see, I'm missing one of my, here's a marker. Okay, so this is our OH group here. Okay, let's look up here on our sucrose molecule. How many OH groups do we have?
Seven. 8.
A lot of places for waters to hydrogen bond. And on each one of these 8 locations, that's 3 water molecules pulling on it. 3 water molecules pulling on it. Okay? Trey, stay with me, buddy. Sit up. All right. And that's not the only thing going on here. Okay? If you'll sign back in and put this in your personal file, please. Thank you, sir. Okay? That's not the only thing going on here. We've got these oxygens in the middle of a carbon chain. Oxygens in the middle of a carbon chain. We could represent this like I've got one carbon chain attached to an oxygen and a second carbon chain, like here's one and here's the other. Okay? Well, there's these lone pairs out here of electrons, and so there's the ability of some polar attraction going on there where water molecules can be attracted to those lone pairs. And so every time we have an oxygen in the middle of a carbon chain, there are 2 places that waters can sort of grab hold of and pull on this sucrose molecule. What?
Oh, I got a highlighter.
Do you, Brad?
I do.
I'm encouraged.
Hold on, I got a highlighter.
Okay.
Hold on, wait, can you scroll back up so I can see you guys?
Well, hang on a minute. Have y'all finished drawing this now? Okay. So up here in our sucrose molecule, we've got 3 of those places for that to happen. 1, 2, 3. Well, that's a lot of places on this molecule for water to grab hold of. Okay, 3 at each one of these OH groups, and I've got 8 of those. So that makes 24 handholds, you might say. Okay, if I'm trying to pick up something heavy by myself, I might not be able to do that. But if I get a lot of guys to come help me, a lot of handholds, we pull it out, pick it up, and move it around. What?
Somebody get a yellow highlighter right here.
Okay. And so we've got 24 of these, and then 6 more here. That's 30 different places for water to grab hold of that water, that sucrose molecule, and pull it out of a crystal and into solution. Much the same way that we talked about earlier, that ionic compounds get pulled out of the crystal formation and into solution. But it's a different process. It's not an ionic attraction to polar molecules. It's polar to polar. Okay? All right, so if we were to have a sucrose molecule, a sucrose crystal, then we could draw it just like a box, I suppose. Okay? This is our sugar or sucrose. Okay? A crystal of it. The water molecules then can pull sucrose or sugar molecules apart from the crystal through these polar attractions and hydrogen bonding. And this is also called solvation. So this whole thing we're talking about here is the solvation. But it's a different kind of solvation. It's solvation of polar solutes by polar solvents. Okay? Once all these locations have hot waters attached to them, you've got a solvated molecule. The process of pulling it apart and attaching all these waters, that process is called solvation. Okay? Does that make sense?
Mm-hmm.
Okay.
Wait! What do you mean by that?
Hmm?
It's alright.
A sugar crystal.
Not like old people.
Or am I just talking?
People can't do that.
You ever look at sugar in your...
Yeah, like a cube.
Yeah.
A sugar cube.
Not a sugar cube, but if you look at an individual crystal of sugar from a sugar bowl, it forms a kind of cube. It looks like a cube. Okay? Huh? A sugar cube is a bunch of those little tiny crystals kind of pushed together. They're not really, it's not a huge crystal of sugar. It's just kind of pushed together. It's, kind of a clump, if you will. Okay? That's why it falls apart pretty easily when you crush it. If you actually had a crystal of sugar as big as a sugar cube, it'd be hard to crunch it with your fingers and make it fall apart. Okay?
Cool.
All right, you got it,
Cool.
Kenya? All right, good.
Okay, cool.
Now, last category then we're going to talk about today, solvation of...
And then we'll be done.
No. Okay, nonpolar solutes by nonpolar solvents. Okay?